Hi, my name is Ben Owens. In this video, we are going to introduce confidence intervals. To get us warmed up and ready for some of the things we will see in this video, I'd like to do the following problem. Suppose that the test grades for a large class were found to be approximately normally distributed with an average of 80 and a standard deviation of 5. What scores will the middle 90% of the data fall between? Now, this is a problem that involves using the normal distribution, and it's one in which we use the area to find an x value, or the scores that we need. And so this is how we would approach this problem. We're given that the information is normally distributed, and they tell us that the average is 80 with a standard deviation of 5, so our step sizes will be 5, and so we take steps of 5 to the right and steps of 5 to the left. And what they're looking for is to find the x values that will give us the middle 90%. And so what we're doing is we're looking for the x values, that is the number here and the number here, that would give us the middle 90%. Well, the way we figure this out is we think about what is the area if the middle 90%, or if the middle is 90%, what is the area left on the outside? Well, between both of these is going to be 10%, so if we consider just the area to the left, that would be 5%. So in order to find the x value that gives us this 5%, we first have to find the z value that gives us that. So looking up the closest thing we can to 0.05 on the normal distribution table, we find that that would give us a z value of negative 1.65. Since the normal distribution is symmetric, then the value here on the right-hand side would be positive 1.65. Now these are the z values that give us the areas that we're looking for. However, we want to find the x values for this. Now the way we do that is we use the unstandardizing formula. That is, here is the formula for the z-score. If we were to take this formula and solve it for the x variable, we get a new formula that looks like this. Using this formula, we can find the x values that will give us the middle 90%. That is, if we take x is equal to the z times the standard deviation plus the average, that would give us a lower bound of 71.75. Doing the same computation for the right-hand side, here we get our z value times the standard deviation plus the average, and that gives us 88.25. So our final answer would be that 90% of our data are going to fall within the range 71.75 to 88.25. Mathematically speaking, oftentimes we call this number our lower bound, and this number we would call our upper bound. Now we're ready to start talking about confidence intervals. Confidence intervals are a major tool used in inferential statistics to make predictions about a population parameter using statistics from a sample. We use confidence intervals in the news and in scientific research, in scholarly articles, and in public opinion polls. I find that students really like learning about confidence intervals, first of all, because they're very useful and they're very much seen in day-to-day life, but also they're actually pretty easy to use. Using confidence intervals is basically just using a formula. And so in this video, we are going to be developing that formula. A lot of the things that we're going to see throughout this video are a little more complicated than you would normally do for using confidence intervals. Typically, using confidence intervals is simply a matter of applying a formula, which most students kind of like. But let's see a few real-world examples of confidence intervals. In this image, we're seeing the percentage of Americans who have tattoos by age group. So here they're telling us that for people between the ages of 18 and 24, 22% of them have tattoos. But for the age group between 25 and 29, 30% of Americans in that age range have tattoos. Now here is the interesting thing. Notice that this article is saying that this is the percentage of Americans, which imply the percentage of all Americans who have tattoos. Yet, if you read the fine print here at the bottom, notice that this is saying that it's coming from a survey of only around 2,000 adults. So what's going on here is we have these numbers that are generated by this survey that only had 2,000 adults, yet they're telling us that these numbers are valid for all Americans. Now, who's to say that this is true? Well, it turns out that studying confidence intervals shows us how we can make these claims. That is, how we can claim these numbers are valid for all Americans when only actually considering a small sample. Here is another example from the news where we see these confidence intervals. Notice that in this case, it's asking, would you support or oppose a state constitutional amendment to legalize medical marijuana? Now, I'm supposing that this is coming from the state of Florida since it's the Tampa Bay Times. So as we see here, from their survey, they found that 68% support and 24% oppose and 8% are not sure. However, if you look at the fine print here off to the side, notice that they're telling us that these numbers have a margin of error of plus or minus 3.9%. What they're basically saying is they think that there is 68% of people who would support this, but this number could be off by as much as 3.9%. The margin of error gives us sort of some wiggle room or maybe a fudge factor for each of these numbers. Anytime you have a margin of error, that is because the statistics that we're looking at are coming from confidence intervals. So what we're going to see in this video is how margins of error are produced and where they come from. So let's look at this guiding example. Suppose a researcher wants to know on average how many Facebook friends the students on a college campus have. What the researcher is looking for is a population parameter, that is an average that we'll call mu. This is the number that we would get if we asked every single person on campus how many friends they had and found the average of those numbers. Now, in order to get the exact average, mu, what would the researcher have to do? Well, clearly, he would have to take the time and effort to ask every single person on campus. Clearly, asking every single person at the college is not feasible, and as we'll see, it's not necessary. Using confidence intervals, we can actually find a good approximation for mu by only taking a relatively small sample. So suppose that this researcher takes a sample of 150 students from the college, and he finds that in that sample, the sample average is 795 and the sample standard deviation is 124. Now, what can we say about the actual average number of Facebook friends for students at that college? Well, we don't know if it's exactly 795, but thinking about the law of averages, we would expect that the actual average is going to be close to 795. The problem is, if we were to take a different sample of 150, then we would probably get a different sample average and standard deviation. In fact, every time we took a different sample, we would expect something that's slightly different from our sample average and sample standard deviation. What we would notice, however, is that the sample averages tend to be around the same number. Maybe not exactly the same, but around the same value. So to kind of think about how this would look, or how to picture it in your mind, what we have is this entire population, that is all the students at the university or the college, that we are looking at. And we're trying to find this number mu. That is our population parameter, the value that you would get if you asked every single person. Well, we don't know exactly what that is. What we do is we take a small sample from that population. Now, from that sample, we get this value of x bar, which is our sample average. That is, this is the average of the data that we collected. Confidence intervals use this sample statistic, that is x bar, to predict the population parameter. So in our example, what we know is this. X bar is equal to 795, and S, the sample standard deviation, is equal to 124. These statistics are found from looking at the data that we collected. Now, the best guess that we have for mu based on our sample is x bar. This is the value that we call the point estimate. That is, the point estimate is the best prediction that we could have based on the sample that we took. So can we say that the average of the population mu is exactly 795? Well, of course not. 795 came from this specific sample. If we took a different sample, we would probably get a different point estimate. But we're probably fair, we can probably say that the population parameter is close to 795. Since the data taken from the sample may not be exactly representative of the population, we need to give ourselves some wiggle room. This wiggle room is what we call the margin of error. That is, in our example, 795 was our point estimate, which is going to be right in the middle of our confidence interval. Taking steps to either side is going to give us this margin of error. Putting those together gives us what we call the confidence interval for our prediction. Now let's just suppose that the margin of error for our prediction is 25. Later in the video, we're going to talk about how we can actually compute this value. But for now, let's just assume that the margin of error is 25. What that would tell us is that if we took 25 to the right, or if we added 25 to the average, that means our upper bound is 820, and subtracting 25 gives us 770, which would be our lower bound. This would be our confidence interval, and there are a few ways to write this. One way of writing it is to say that the confidence interval is equal to 795 plus or minus 25. This is the point estimate plus or minus the margin of error. Another way of writing it, and this is the way I prefer, is to actually write this as an interval, where we have our lower bound, comma, our upper bound. In general, we can think of confidence intervals as this. It's always the point estimate plus or minus the margin of error. Or, if we wanted to see it written in interval notation, it would be the point estimate minus the margin of error all the way to the point estimate plus the margin of error. So let's look at this next example. A researcher collects data to estimate the average weight of cats in a certain city. His data produce a confidence interval of 4 to 11. Now from this, what can we say is the point estimate and the margin of error? Notice what we're given here is the lower bound and the upper bound for this margin of error. So here is what we know. If we were to draw this out, we know that the lower bound is going to be 4 and the upper bound is 11. Now the margin of error is always going to be smack dab in the middle of the confidence interval. And so we can find this, the point estimate rather, by taking the average of the upper and lower bound. That is, adding up 4 plus 11 dividing by 2 gives us 7.5. That is our point estimate. The margin of error can be found by seeing how far the point estimate is away from the upper bound or the lower bound. This, in this case, is simply 3.5. You can also get the margin of error by taking the difference of the upper and lower bound, so 11 minus 4, and dividing by 2, which would give you 3.5. So let's go back to our example. How do we go about calculating this margin of error? So notice here, what we're going to ask is to find the 95% confidence interval. In order to find that, we need to be able to calculate that margin of error. Well, the margin of error is based on the sampling distribution. So we'll be using the sampling distribution in order to figure out what this margin of error needs to be. Now, the formula for our confidence intervals looks something like this. Now, I know that this is kind of complicated, but what we're going to do is later in the video, we're going to go back and talk about what each of these pieces mean, or how we would go about using this formula. In fact, we will be developing this formula based on a general process. Now, recall that when we have a sampling distribution, if the sample is large enough, then we can say that the sampling distribution will be approximately normal with an average of mu and a standard deviation of sigma divided by the square root of n. These are the values that we're going to use when dealing with our confidence intervals. So here is what we know. The confidence interval is going to follow or answer the following question. What values will give us the middle 95% of the sampling distribution? Now, this is basically asking us to do one of those problems that we had in our warm-up to this video. That is, we're looking for the middle 95% of some sort of normal distribution. Now, since we don't know mu and sigma, we're going to use x bar and s in their place, so we could say that our sampling distribution is going to have an average of 795 and a standard deviation of 124 divided by the square root of 150, which is around 10, a little over 10. So, since our sample is big enough, we know that it's going to be normally distributed, and we can sort of approximate our average and standard deviations here away. And so we're looking for the values that are going to give us the middle 95%. Now, thinking about the problem that we saw in the warm-up, in order to find the middle 95%, we would need to find the z values first. Now, these z values, negative 1.96 and positive 1.96, can be found by seeing what area gives us 2.5% on the left and the right. Or in other words, looking up these numbers on the normal distribution, we would need to look up the closest thing to 0.025. Doing that would give us the z values of negative 1.96 and positive 1.96. Now, unstandardizing this, that is, if we take these z values times the standard deviation plus the average, that gives us our lower bound. And doing that on the right-hand side gives us the upper bound. This is what we would call our 95% confidence interval. So what this is saying is we're 95% confident that the actual average, that is the mu value that we're looking for, is going to be somewhere in between 775 and 814. So now we're going to take some time to develop this confidence interval formula. In mathematics, often when you're given a formula to work with, it's simply what comes out of following a procedure but using variables instead of actual numbers. So what we're going to do is we're about to go and do the process that we just worked, but using variables instead. So suppose that we take a sample of size n from a population, and that sample average is x bar and the standard deviation is s. Now, in the last problem, of course, the value of n was 150 and the average was 795 and the standard deviation was 124, but in this case, we're simply going to leave those as variables. So we don't know what these values are, but we're just going to leave them like they are. Now, what we want to do is find the p% confidence interval. Now, when dealing with confidence intervals, we can actually set the level of confidence. So a lot of times we'll be finding the 90% confidence interval or the 95% confidence interval or the 99% confidence interval. In this case, we're just going to leave that as a variable. That is, we're just going to leave it as the p% confidence interval. So the question that we really need to answer is, what values will give us the middle p% of this sampling distribution? So assuming that the sampling distribution is normally distributed, and we're looking for the middle p%, then we can say that on the outside, there's going to be a certain amount. Now, when considering the middle p%, we often refer to the outside percentage as alpha. That is, the percentage that we have left over to the left and to the right are what we call alpha. So in our last example, the middle 95%, the alpha was equal to 5% or 0.05. Now, of course, since we have to take that amount and split it in half, on either side, we will be left with alpha divided by 2%. So here we would think that we would have alpha divided by 2, or that's the variables that we would use to describe those. Now, in the process, the next step was to find the z-value associated with these. Since we're working with variables, it's not like we can look up the number, so we're just going to write that as negative z sub alpha over 2 and positive z sub alpha over 2. In other words, these numbers are going to represent the z-value associated with an area of alpha over 2 to the left, and the z-value associated with the area of alpha over 2 to the right. These z-scores we simply call z sub alpha over 2. So let's continue on with this process. If we know that the average here is going to be x bar, and the standard deviation is s divided by the square root of n, because it's a sampling distribution, and we know that our z-values are going to be called negative z sub alpha over 2 and z sub alpha over 2, unstandardizing this, we would get that our x value, that is our lower bound, is equal to negative z sub alpha over 2 times the standard deviation plus the average. And our upper bound, this value of x, would be z sub alpha over 2 times the standard deviation plus the average. If we were to look at these, kind of rearranging them, we get that this lower bound is equal to the average, which is our point estimate, minus z sub alpha over 2 times s divided by the square root of n. This is our margin of error. And then the upper bound, of course, is simply x bar plus that same value, that margin of error. Putting these together, we get our confidence interval formula, which is x bar plus or minus z sub alpha over 2 times s divided by the square root of n. Now here is the nice thing. Now that we have a formula to work with, since we left everything as a variable, that means that we can simply apply this formula to any situation. That is, we can take whatever numbers we want and plug them into these places, and that will give us our confidence interval. We're actually going to be using 3 different formulas for confidence intervals, and they'll depend on the situation. If we have a large sample, then we're going to use the confidence interval that we've been using before. However, if our sample is smaller, say less than 100, we're going to be using this other confidence interval. Now notice the only difference is that this involves t sub alpha over 2. So that'll be dealing with the t distribution. Finally, if we're using proportions, we'll be using this formula for confidence intervals. We'll be looking at some examples of these different types of confidence intervals in our next video. So here we are wanting to find the 99% confidence interval for the same situation that we saw before. Instead of going through that long process, however, we're simply going to use our formula. So we know that since this is a big sample, we can use the formula here. The confidence interval is equal to x bar plus or minus z sub alpha over 2 times s divided by the square root of n. Now just reading the problem, we can say that x bar is equal to 795, the sample standard deviation is equal to 124, and the size of the sample is 150. The only thing that we are left to look up is the z sub alpha over 2 number. Now this value we can actually find on our normal distribution table, and in fact it's in a special place there on the bottom left-hand corner that actually tells us these values. Looking at that, For a 99% confidence interval, we can say that this number is going to be 2.575. So now we have all the values that we need in order to build our confidence interval. So plugging in those values in the appropriate place and then working this out, what I like to do is usually to multiply all of these numbers on the right to give us our margin of error. We would get that our confidence interval is 795 plus or minus 26.07. If we wanted to write this as an interval, we would simply subtract 26.07 from 795, which would give us 768.93, and then add that same value to 795, which would give us 821.07. Now, what we found is that we are 99% confident that the actual average number of Facebook friends on this campus is somewhere between these two numbers, between 768 and 821. This is our 99% confidence interval. I hope this video has helped you to understand confidence intervals and, moreover, where this formula for confidence intervals comes from. Thanks for watching.